Hello everybody, this is Gary Mrozinski, and this is part C of Chapter 7. Chapter 7 of the Microeconomy Today by Schiller and Gebhardt, published by McGraw-Hill. We're back to our genes example, and we're getting an understanding of the shapes of the cost curves. That's what we're doing in this chapter, because then in the chapters after this, we're going to be adding those curves to the graph of supply and demand for pure competition, monopoly, oligopoly, monopolistic competition. So we need to understand the shapes of the cost curves. That's what we're doing in this chapter. And the big concept that we developed early on was the law of diminishing returns. Just to remind you, this says that as you increase output, you need to add variable resources to your fixed plant in the short run. This is all in the short run so far in this chapter. In the short run, the only way to increase output is to hire more workers or increase labor hours, and your fixed plant is fixed. You don't have time to increase it. As you do that, output will increase. As you add more workers to your fixed plant, they'll produce more per day, but smaller amounts the more workers you add. So this then helps to explain what happens with costs. In this graph, you can see to the left, marginal product is diminishing. And just to remind you what marginal product is. Marginal product, if you increase output by hiring one more worker, then the amount that output increases by when you add that worker is the marginal product of that worker. It's not a linear relationship. Marginal product will diminish. It will go down. The more you increase output by hiring more workers, adding more workers to your fixed plant, the extra output produced as each worker's added goes down and eventually will go negative. In this example, you can see across the bottom, I'm looking at the left graph, across the bottom is number of workers. If you get to the point where you're going to add the 8th worker, you have 7, you're going to add the 8th worker, total output's going to go down, so you would never hire that 8th worker, right? In fact, you would never hire the 7th worker, because the marginal product of the 7th worker, you can see, is 0. You're not producing any more than when you had 6 workers. Well, there's no way to justify hiring the 7th worker then, because that hiring the 7th worker cost you something. So now, let's look at the graph on the right. As you increase the number of workers across the bottom, that's L. Now we're looking at the cost of the extra, what's being added to total cost as you hire one more worker. Total cost per unit this is. Well, it's going up, and it's going up really fast, right? Because the cost per unit, the only way you can increase output is to hire more workers. The workers are becoming less productive on average. Then you're using more labor inputs to produce each unit, which means the cost is going up. And it's increasing at an increasing rate because of the law of diminishing returns. As marginal product decreases with added workers, we continue to pay the added workers, but we get less added product with each added worker. That's a great way of putting it. Therefore, the cost per added product increases as marginal physical product declines. So marginal cost then is the increase in total cost when you produce one more unit. And remember, the only way to produce one more unit is to use more labor. And the labor becomes less productive the more of it you're adding to your fixed plant. So as marginal product goes down, marginal cost has to go up. And vice versa in the very beginning, when you have increasing returns, the marginal cost actually does come down. But again, you would never produce at those very low levels of output. So for the region, for our purposes, just think of marginal cost as always increasing at an increasing rate. This example gives you some actual cost numbers, and it kind of makes it more of an applied example where you can see what the different resources are and what the cost per units are. All right, so in this example, you have one factory, And so that's going to be your fixed plant or part of it. And it's costing you $100 per day. So all of this is based on per day, production per day, cost per day. All right, so $100 per day to lease the factory, let's say. All right, so that's $100 of fixed cost. One sewing machine, this is also going to be part of your capital, part of your fixed plant. One sewing machine costs you $20 per day. Let's say you're leasing it, or maybe you purchased it and you're paying on payments $20 per day. Whatever it is, it's costing you $20 per day. That's also part of your fixed plant, part of your fixed costs. You have one operator who costs $80 per day. So that's a variable resource, right? Because you could hire a second worker if you wanted to. So that's a variable resource. If you have one, it's costing you $80 per day. That one worker, then the total cost associated with labor resources is $80. Here are some materials you need to use per day. You're going to use up 1.5 bolts of denim to produce the quantity that you would produce in one day with one operator, and that's $30 per bolt. So that means the total cost of materials is $45. That's a variable resource, right? So now you can see down below we're separating this into fixed costs and variable costs. And your total fixed costs are $120. Your total variable costs are $125. So your total costs then are $245. The costs in the previous example we just went through are in this table. So Q is all the way to the left. We had one worker producing 15 pairs of jeans per day. So that's a certain level of output. That is, let's see, the third row in this table. See where Q is equal to 15? All right, so go across the table. Fixed costs were $120. Variable costs were $125. Total cost then, if you're producing 15 jeans per day, which is what you would produce with one worker, $245. Average fixed cost, you're just dividing 120 by 15 is 8. Average variable cost, you're just dividing 125 by 15, $8.33. Average total cost, $16.33. All right. Now you can produce 10 if you want, 10 jeans per day. I guess you would use not a full-time worker, right? You would use a part-time worker to do that. But you could do that. Well, the cost will change because your variable resources will change. Your fixed costs never change. So it's $120 no matter how much you're producing per day. All right, so what if you go from 15 pairs of jeans per day to 20 pairs of jeans per day? Again, you can see how all of these costs are changing. So let's look at the average cost curves, or data that would become curves once we graph them. All right, average fixed cost, that's interesting. It's the largest if you're producing, the first row, 10 per day, and then it declines sharply. That makes sense because you're dividing $120, your fixed cost, by more and more units of output. You're spreading those costs over more units of output. So average fixed cost, if you're to graph it, is very easy to understand. It starts high and it gets low, and it approaches the x-axis because you're spreading, again, those fixed costs over more units of output. How about average variable cost? Well, it looks like it comes down in the very beginning if you're producing small amounts of output. It reaches a minimum and then it rises. It has a U shape. That is a characteristic of the average variable cost curve. It is U-shaped. It goes down in the beginning as you're increasing Q. As you go down this table, from row to row to row, you're increasing output. Well, it's decreasing in the very beginning. It reaches a minimum, so that would be at Q equal to 20. And then it increases at an increasing rate after that. That's because of the law of diminishing returns. Now, average total cost, all you're doing is adding together the prior two columns, right? Average fixed cost plus average variable cost for every Q, every row in the table. You're just summing them together. So it's also going to be U-shaped. And it decreases mostly in the beginning because average fixed cost is decreasing so rapidly. Then average fixed cost becomes almost insignificant, and average variable cost starts to define the shape of the average total cost curve, and it increases as average variable cost increases. And when we show these on a graph, this will be more clear to you. But we're just trying to understand quantitatively why the shapes of these curves look like they do. All right, but the next slide we're going to focus in on graphing the total cost curves. So that's sort of the first part of this table. Fixed cost plus variable cost equals total costs. Fixed cost, no matter how much you produce, $120. That's going to be a horizontal line on our table because it's not changing as Q goes up. Variable cost increases first at a decreasing rate and then at an increasing rate as you're experiencing diminishing returns. Then we're going to sum them together. So let's see what the shapes of these curves look like. So here are the total cost curves. And I'm going to say at this point, these are actually not that important to us because we're not going to use these curves for our analysis. But just one time, just to show you what they look like, here's what the total cost curves look like. Remember I told you fixed cost, that's the easy one to understand. It's $120 no matter how much you're producing. So as you go across from left to right in this graph, you're increasing the number of genes you produce per day. No matter how much you produce per day, it's $120. It's a horizontal line for that reason. Now the blue, the light color blue curve that starts at the origin, that's total variable cost. Total variable cost is 0 if you're producing 0 genes per day, right? Total variable cost increases the more you produce. You expect that, right? That's the cost of your labor. But it increases at a decreasing rate and then increases at an increasing rate. This is, remember, variable cost per unit you're producing. And as the units you're producing is increasing, you increase at a decreasing rate because you're experiencing increased returns. Workers, on average, are becoming more productive just in the very beginning, but then beyond some point, they become less productive on average. And so variable costs increase at an increasing rate. Now, what's interesting here is that curve, you can see, almost becomes vertical. Why would that be? Well, because there's some maximum capacity that your fixed plant can produce, right? It's defined by the size of your fixed plant. This is in the short run. And it looks like it might be something like 50 pairs of genes per day or something like that. And so no matter what you want to do, how many workers you're going to hire and put in this facility, that's the most you could produce. And so that's almost like a a vertical barrier that you cannot exceed. So these curves start to become vertical. So then for total costs, you're just going to sum together vertically the green graph and the light blue graph. And all that does is offset the light blue graph by $120 vertically. You're just shifting it upwards by $120. And that's your total cost curve. It's S-shaped in the beginning between point A and B. It increases at a decreasing rate because you have marginal product is actually increasing the more workers you hire in the very beginning with small amounts of output. Then beyond point B, the law of diminishing returns, the law of diminishing marginal product says that total costs will increase at an increasing rate because, again, workers are becoming constrained by the fixed plant. These are the curves we're going to get used to drawing or analyzing if you see them, if they're presented to you. These are the average cost curves. Let's look first at the average fixed cost curve. So this is the one that starts way high and then takes a nosedive and continues to decrease, and it gets closer and closer. If this graph were extended horizontally to the right, then that curve would get closer and closer to the x-axis because you're spreading fixed costs over more units of output. So that one's very easy to graph. Average variable cost curve, that's the red graph. Remember, in the beginning, it goes down the more you produce. The cost of the labor to produce a unit is what this is. It's the labor cost per unit produced, because that's the only variable cost we're thinking about right here, right? In the beginning, because of increasing returns, the workers actually become more productive per worker in the very beginning if you have a very small workforce. Then the variable cost, the labor cost per unit, actually comes down. It reaches a minimum at, looks like it's around 20 pairs of jeans, and then it goes up from there. So the average variable cost for most of the range will increase at an increasing rate because of the law of diminishing returns. Because the only way you can go from left to right in this graph is to hire more workers and load them into your fixed plant, which constrains you. The productivity per worker goes down, so that means the labor cost per worker goes up. Or I'm sorry, labor cost per unit produced goes up because you're adding more workers, but the total department is producing fewer. The increase in output is getting smaller and smaller the more workers you put in. All right. So then the green graph is just the vertical sum of the blue graph and the red graph. You're just going to at every Q, look at 20 for example, Q equal to 20 on the x-axis. All right, so it looks like, I don't know the exact numbers here, but it looks like average fixed cost is 6, average variable cost is a little below 8. Add those two together and you get 13 point something, point K. So you're just summing vertically the blue and the red graphs to get the green graph. So the green graph, the average total cost curve, this is all you need to remember then, is U-shaped. This is just a different set of data showing you the same. I prefer these curves. They're a little smoother and it's a little clearer understanding the shapes of these curves. The next couple of slides you're going to see. All right. So again, total fixed cost is going to be some constant amount no matter how much you produce. That's the red graph. These are the total cost curves. What would this be? Like a light blue or teal? Would you call that teal? The total variable cost curve. The light blue curve or aqua. It's S-shaped. It increases when you go from left to right. It goes uphill, but it increases at a decreasing rate initially, and that would be because of increasing returns, decreasing marginal product. Then beyond some point, it looks like Q equal to 3. Beyond that point, total variable cost increase at an increasing rate because of the law of diminishing returns. You're just summing together then the red curve and the aqua curve to get the electric blue curve, I'm going to call that, and that's total cost. You're just summing those together vertically. So you just need to offset your variable cost curve by 100, and then you get the electric blue curve, which has the same shape as total variable cost. Again, we're not going to use those cost curves for our analysis. We're going to use the average variable cost curves, and these are those. All right, so we have average fixed cost, the green curve. It starts high, it takes a dive, and just continues to decrease and decrease because you're spreading your fixed cost over more units of output the more you produce. Average variable cost, that's the tan curve or gold curve. It decreases for low levels of output and then reaches a minimum. And remember, you would never produce that low a level of output. It wouldn't be profitable, but that's what would happen. And then it increases, it looks like beyond 5 units per day. Increases at an increasing rate. Average variable cost increases at an increasing rate because of the law of diminishing marginal product. And then you're just summing together the green curve and the gold curve to get the red curve. We add in now the marginal cost curve, which in this graph is aqua. Now, an interesting feature of the marginal cost curve, this will help you to graph it if you ever needed to graph it. It intersects the average variable cost curve at its minimum, the bottom of the U. See that point? And then it also intersects the average total cost curve at its minimum. So just make a little point at the bottom of the U, that is the ATC curve, and then make another little point at the bottom of the U, that is the AVC curve, and you know that the marginal cost curve must go through those 2 points. And then it increases at an increasing rate. And you can see in the very beginning, marginal cost decreases again because you could have increasing returns. It doesn't always do this, but in most examples we show this. You have increasing returns, it actually makes marginal costs go down, and then it increases at an increasing rate. One more time, I'm going to remind you what marginal cost is. As you increase output, you're going from left to right on this graph. Total cost is increasing by some amount. Marginal cost is the increase in total cost when you go from 5 to 6, and 6 to 7, and 7 to 8, and 8 to 9. The amount that total cost changes is the marginal cost. It's the change in total cost when you increase output. And you can see that it is increasing at an increasing rate, again, because of the law of diminishing returns. So to summarize, this is the average total cost curve. In some cases, we're only going to draw this one curve. All right, so the average total cost curve is U-shaped, and why is it U-shaped? There's 2 parts to the explanation. In the beginning, remember where this comes from. So average variable cost plus average fixed cost gives you this curve. So you're summing those 2 curves together vertically in dollars, right? Well, at low levels of output, as you go from 0 to 1 to 2 to 3 to 4, average fixed cost is very high. It's a really high number because let's say you're producing 1 unit per day. Your average fixed cost is the same as your fixed cost, right? It's very expensive per unit in your fixed costs. But as you produce more and more, your fixed costs get spread out over more units of output to give you average fixed cost. And so it takes a nosedive. So in the beginning, the average total cost curve is mostly influenced by the average fixed cost curve because it's so high. Then, after some point, average fixed cost gets so small, it becomes insignificant. And it's the average variable cost that mostly influences the average total cost curve. So in the beginning, average total cost decreases because average fixed cost is decreasing so quickly. Then, beyond some point, average total cost will increase at an increasing rate because average variable cost is increasing at an increasing rate because of the law of diminishing marginal product, the law of diminishing returns. Now, the term efficient scale is that level of output, in this problem that would be 5 units per day, where average costs are minimized. Average total cost is at a minimum if you're producing 5 per day. So I'm going to ask you this question. Does this mean we should produce 5 per day? It certainly seems that way, right? Come follow me down the path to the wrong answer. It's right over here. It's over my shoulder. Come follow me. Yeah, I'll be like the devil over your shoulder. Sure, it must mean that if you produce 5 per day, that's the best place to be, right? No. We don't know enough. We're not given enough information here, right? We only know about costs. Any business firm, we assume, your primary objective is to maximize total profit. We can only understand profit if we have revenue information. So far, we only have cost information. In this whole chapter, we're only addressing costs. When we get to the next chapter, we're going to start to introduce revenue per unit, which is just the price, right? You would need to know something about revenue to know what level of output. This is just one piece of information. And here's a spoiler alert. It is rarely efficient scale where you're the most profitable in total profit. It is where you're the most profitable per unit produced, but that's not what your goal is. You're not trying to maximize profit per unit. You're trying to maximize total profit. But anyway, that's a subject that we'll return to later. Now, what I just explained about the shape of the average total cost curve is explained here as concisely as I could type it. And so you can take a look at this slide to remind you why average total cost is a U-shaped curve. This slide is explaining the point where you reach efficient scale, where average total cost stops declining and starts to increase. And again, explaining that this is not necessarily where you want to produce. It's where profit per unit is maximized, but we don't know if it's where profit total is maximized. I mentioned that the marginal cost curve intersects the average total cost curve when it's at its minimum, at the bottom of the U. That's also true for average variable cost. I'm going to take a crack at trying to explain to you mathematically why this would be, and I'll explain at this point that if you don't quite grab this, I'm going to present this as an analogy. If you don't quite absorb all of this, it's not going to doom you. You're still going to do okay in this chapter if you don't quite get this one concept. And then just remember that marginal cost does intersect at the bottom of the U. If you don't understand why that happens quantitatively, why that would be the case, then I wouldn't sweat it. All right? So here's an analogy. Imagine that the average total cost curve is the equivalent of your cumulative GPA. All right? And then the marginal cost in this analogy would be the grade you get on the next course you take. Right? This is marginal analysis. That will affect your cumulative GPA, right? If the grade you get on your in your next class, which would be this class, let's say, is higher than your cumulative GPA, it makes your GPA go up. If the grade you get in your next class is lower than your current cumulative GPA, it makes your GPA go down. The same is true with marginal cost and average total cost. In the region of the curve where marginal cost is below average total cost, when you go from left to right, and Q is increasing, and Q is the courses that you're taking, it's making average total cost come down because marginal cost is below it as you increase Q. When you get to the region of the graph where marginal cost is above average total cost, greater than average total cost, it's making your average total cost go up for the same reason that the grade on your next completed course, is going to make your cumulative GPA go up. Again, if you didn't quite absorb that analogy, don't sweat it. Just memorize, remember that the marginal cost curve intersects at the bottom of the U, the bottom of the average total cost curve U and the average variable cost curve U. Here is a more standard and straightforward explanation for the shape of the marginal cost curve. Remember, diminishing returns cause marginal cost to increase as output increases. But in the beginning, there's a brief drop in marginal cost at low levels of output. You have increasing returns. But then it starts to rise rapidly as output increases, because the only way you can increase output is by introducing more variable resources to your fixed resources, more workers to your fixed plant. And on average, they become less productive. So then the labor cost per unit produced starts to go up, and that makes marginal cost go up. All right? And marginal cost, again, intersects average total cost at its minimum point at the bottom of the U. And you can see an explanation for why that's the case. So far, you've been talking about the short run. Now let's think about the long run. In the long run, you have time to adjust the size of your facility, right? To increase your fixed plant, to buy more land if you have to, or to add on to your manufacturing plant or your office building, whatever it is, or maybe to build a second office building, whatever it is, but to increase your fixed plant, which gives you more capacity, right? And this changes the shape of your cost curve. So that's what we're going to talk about here. In the long run, there are no fixed resources. All resources are variable resources, including the size of your facility and the land you're using. So these curves you see in this graph are short-run average total cost curves. So imagine, look at the curve furthest to the left. All right? This might be your average total cost curve that you start with. You're producing in a small manufacturing plant, and maybe in this example, if you're producing 40 units per day, 40 pairs of jeans per day, you're doing okay, right? You're near the bottom of the U. But what if you're producing 60 per day? Again, only look at the first curve, that first U-shaped curve. Well, look at where you would be. You're in the dashed region of that curve. Your average total cost, the per unit cost to produce your jeans, is actually pretty high now. You might think about increasing your plant, the size of your fixed plant. You might think about building or maybe expanding your existing plant into a medium-sized plant. All right? And I realize that's a very generic term. What do you mean by medium-sized? Well, it's bigger than what you have, right? If you build a medium-sized plant, then your average total cost curve in the short run might look like that second curve. So it's U-shaped also, except it reaches a minimum at a larger rate of output. It looks like maybe, 80 pairs of jeans per day is the bottom of that U, the medium-sized plant curve. Again, that's a short-run average total cost curve that you might have if the size of your plant were medium-sized. All right, so that means that you've increased your capacity. So if you plan to produce 80 per day, that's the size plant you would want, right? And in fact, if you're going to produce any level of output beyond point A, which looks like that's 50 pairs of jeans, and if you could choose between a small-sized plant and a medium-sized plant, at that point you would want to start producing in a medium-sized plant. In the long run, you would make that decision, right? Because for every level of output, for every cube belong, let's just say 60 pairs of jeans per day. If you had your choice between producing in a medium-sized plant and a small plant, look at what your average total cost would be. It'd be much lower, much smaller with a medium-sized plant. All right? And in fact, that would be true all the way up until point B, whatever level of output that is. And I'm going to guess that that is 110 jeans per day. Something like that, point B on the x-axis. When you reach that point, your average total cost is rising. You're starting to reach your maximum capacity. So the cost per unit's going up. Then if you could choose to produce in a large size plant, you might do that. In the long run, you can choose to produce in a large size plant. You have time to increase the size of your plant or maybe build a larger one and move into it. All right? Then your average total cost curve in the short run would look like that third curve. It reaches a minimum at a much higher level of output, point C it looks like maybe, right? So again, these are short run average total cost curves that are different for different size facilities. Well, in the long run, you can vary the size of your facility. So your long run average total cost curve then looks like the darkened U-shaped curve that you see there. And it is comprised of the average total cost curves in the short run for various size facilities. Now, we only looked at small, medium, and large. Well, there could have been a size that's somewhere between small and medium, like a junior medium or something like that size facility. Its cost curve would fit in between small and medium. And you could visualize where that would go, right? And maybe there's a size facility that's between medium and large, like a junior large size facility. Then its cost curve would fit between those two. And who says that those are the only size? There's an infinite number of sizes of plants you could choose to produce. That's what these dashed curves are, this multitude of U-shaped curves. These are short-run average total cost curves that you could choose from amongst for different size facilities. You could choose any size facility you want. And so then they become, the aggregate of these curves become the long-run average total cost curve that is the darkened U-shaped curve that you see there. That's the long-run average total cost curve. It is also U-shaped, and we're going to discuss why that would be the case. First of all, as you grow and get larger and larger in the long run and increase the size of your facilities, your costs are going to go down per unit because of what's called economies of scale. You're going to experience economies of scale. Your average total cost goes down in the long run. And all of the reasons that the Industrial Revolution was a good idea, all of the benefits of the Industrial Revolution are economies of scale benefits. All right? Mass production versus small batch mode. So we were talking, when we talked about the Industrial Revolution in the macroeconomics course, we were talking about the transition from the cottage system of producing to the factory system of producing in larger scale in a facility that's especially designed for producing, and you can optimize the flow of materials, what's now called industrial engineering, and think about the flow of materials through your facility and the equipment. You can afford more expensive capital, right? More powerful machines and automation. If you're producing on a very small scale, you can't afford that. It's called efficient capital. You don't experience efficient capital. The larger you are, the more you're able to afford, because you're spreading those fixed costs over more units of output. And so those are efficiencies that lead to economies of scale. Labor specialization is huge. If you break down the production process into smaller steps and assign workers to do just more narrowly defined jobs, just maybe step 1 and 2 of a 12-step process, and someone else does step 3 and 4, this is division of labor, labor specialization. You can do this with lower skilled workers. They can be trained more quickly. You can pay them less. So labor costs go down, and they can produce, the whole system will produce more per unit time than if one person were producing the whole product. That's labor specialization. This makes your costs go down, cost per unit. These are reasons for economies of scale. This applies to management of the organization too. A supervisor can handle 20 workers, and in a very small plant there might only be 10 workers. Well, then the supervisor is being underused. Same thing for other administrative positions in the organization, like marketing and human resources. And I mentioned efficient capital. So these are all reasons for economies of scale, meaning as you grow in the long run and increase the size of your facilities and increase your capacity and produce more and more per unit time, per day or per month or per year, your average total cost goes down. But then you reach a minimum point, and then your average total cost starts to increase. Now, this might not be as obvious to you, but this does happen. This is known as diseconomies of scale. So now, you're already very, very big. If you continue to grow in size, average total cost is actually going to go up. And think of any very, very large organization. I hate to say this. I worked for the federal government very early in my career, and that's a very large operation, right? The U.S. federal government, one of the largest organizations in our economy, and I think we're experiencing diseconomies of scale. So we've gotten to the point where getting any larger is going to decrease productivity and the costs per unit of whatever it is we're producing with the federal government. All right, this is what you could experience. Worker alienation, you feel like you're just a number. That affects morale, and morale affects productivity. Rigid corporate structures emerge. Have you ever heard the term bureaucracy? Off-site management may be unresponsive. In a large plant, one person can't assemble, digest, and understand all of the information essential decision-making on a large scale. The plant manager, it becomes very difficult to manage. Authority gets delegated to many vice presidents, second vice presidents. Again, think of the structure of our federal government. So the management hierarchy becomes costly. Communication problems, bureaucratic red tape, which costs you money. But even in private industry, diseconomies of scale happen. And I'm recalling a quote that I read one time from the CEO of General Motors, and he was speaking at an industry association event, some sort of annual conference of the automotive industry. So all of the competitors that were there, and what he was saying, he was saying it with sort of a sense of self-deprecating humor, but I think all of them understood what it was. General Motors being the largest of the U.S. auto manufacturers, he said, General Motors is such a huge monster that when you shake its tail, nothing happens at the other end for months and months. It's so large that there's no way to really management. You just try to keep track of it, which again, I hope is not literally true for General Motors' sake, but this is the point he's making. It becomes so large and so difficult to manage and to communicate within that you experience diseconomies of scale. Now, there are some types of industries where increasing the rate of output, increasing the size of your facility doesn't necessarily decrease average total cost. If that's the case, then there's a range of output for which you have constant returns to scale. I'm looking at the first graph on the left here. Economies of scale are where building a larger facility lowers your average total cost curve. And so these are short-run average total cost curves for different size facilities. That's what we're doing here, right? So the middle panel shows you a graph where increasing the size of your facility does give you economies of scale. And then again, diseconomies of scale are where you increase the size of your facility and now your average total costs are going up. Constant returns to scale again are when increasing the size of your plant does not necessarily lower your costs per unit. And this is a characteristic of certain kinds of industries that are not particularly capital intensive, like retail, or how about McDonald's? McDonald's, you might think, there's so many McDonald's around, why isn't there just one McDonald's that produces on a larger scale? Same thing with Dunkin' Donuts. Why are there so many Dunkin' Donuts so close together? Why wouldn't you have one larger one centrally located that could produce at a lower cost? It's because they're experiencing constant returns to scale. Producing out of one larger facility does not necessarily lower their average cost to produce, their cost per unit. And so if that's the case, it doesn't make sense to have one large facility. It's better to have lots of smaller facilities that could capture more customers. So this is the end of Chapter 7. I know there's a lot in Chapter 7. You might want to review this a second time. But this is all about the costs of production. We will then apply everything we learned in this chapter, specifically the shapes of the cost curves, now to the next series of chapters where we're going to be looking at different market structures, where what's varying is the level of competition. So if there's no competition, only one producer, that's a monopoly. That's one kind of market structure. What if there's hundreds of producers, even thousands of producers? That's pure competition. That's another kind of market structure. Those are two ends of the spectrum. And then in between, there's oligopoly. That's a little bit better than monopoly. There's only a few large producers, so if only a few sellers for the consumer to choose from that control most of the market share, that's oligopoly. And then in between oligopoly and pure competition is monopolistic competition. That is the market structure that describes most of the markets in our economy. And so we'll go through each one of these one at a time, again applying these cost curves to each of those kinds of markets, where the goal is always going to be to maximize total profit. All right, I'll see you in Chapter 8.